Thermocouples are widely used for temperature measurement. They are cheap and work across a wide temperature range. The operation of the thermocouple is based on the Seebeck effect. The Seebeck effect refers to the development of a voltage across 2 points of an electrically conducting material when there is a temperature difference between those 2 points. We can write the temperature-voltage relationship as V equals S times T2 minus T1, where S is the Seebeck coefficient for the metal alloy. I can show this using a copper wire. I will heat one end and measure the voltage across both ends. As the temperature drops, so does the voltage. I can't easily put a multimeter probe into a furnace, so I have to use a wire to connect the hot end to my voltmeter. If we use two wires of the same type, the voltages cancel each other. If we use two wires with different Seebeck coefficients, we can leave the junction in the location we want to measure the temperature and measure the ends of the wires. The measured voltage is difference between the voltages generated by each individual metal wire. This is the principle of operation for thermocouples. We can construct a thermocouple out of any dissimilar metals. Here I have a stainless steel rod. I put a couple of turns of copper wire around the rod. When I hit the junction, I see the voltage change. This is basically a thermocouple. Thermocouple manufacturers and metrology standards organizations provide tables for voltage versus temperature that have been measured and interpolated over a range of temperatures for particular thermocouple types. This is a common K-type welded joint thermocouple. Since a contact is sufficient between the wires, the question is whether the wires need to be spot welded. Why not just twist the end of the wires? A junction weld break is not a major problem if you have a good clean contact with the wires at the hot junction area and a strong enough pressure to hold the conductors together. If you do not, then you will get a reading, but it could be in error and significantly in error depending on the contact. Also, if the temperature is high, the wires will become oxidized. The chances are you will get bad contact and an incorrect reading by an unknown factor. Our homemade thermocouple has started oxidizing even after a few seconds of heating. Though the rule is to spot weld the contact and not twist the wires. If the weld breaks and the wires are twisted, there is a possibility of wrong reading. It is better to have an open circuit condition where you can understand the fault rather than continuing to receive potentially bad data or readings. To use a thermocouple with a microcontroller, we first need an analog front-end amplifier to increase the voltage range from the thermocouple from millivolt levels to the input range of the microcontroller's ADC. So a 0 to 100 millivolt voltage range generated by a thermocouple must be amplified to the 0 to 3.3 volts or 0 to 5 volts input range of a microcontroller ADC. Next, we need a high-resolution A to D converter. Microcontrollers typically have 10 to 12-bit ADCs. Given the wide range of temperatures, this is not sufficient. An ADC of 20 or so bits is needed. The next building block is a conversion lookup table with response curves for different types of thermocouples to calculate the temperature from the voltage reading. Next, we have an interface to connect to a microcontroller. This is typically SPI or I2C. The thermocouple voltage is proportional to the difference in temperature between the sense junction T-sense and the reference junction T-ref. The reference junction always exists and may be the connection of the thermocouple wires to your voltmeter. Note that brass, copper, plating materials all form additional intermediate junctions that cancel if they are at uniform temperature. To obtain the desired measurement, it is not sufficient to just measure the voltage across the wires. The calibration curves are provided for a reference temperature of 0°C. We will have to measure the reference temperature in our case and compensate for it if it's not at 0°C. This is normally done by measuring Vref with a temperature sensor such as a thermistor. The Vref is then used to compensate the voltage reading before applying the thermocouple curve. A thermistor is sufficiently accurate to do this measurement. Again, an amplification and accurate analog to digital conversion stage is required. One solution is to use a thermocouple interface IC. The LD100 system supports the Maxim MAX31856 device. This device is available on an inexpensive board from a multitude of suppliers and internally supports several types of thermocouples. I bought a couple from eBay and they all work fine. The MAX31856 performs cold junction compensation using an internal precision temperature sensor and digitizes the signal from any type of thermocouple. The MAX31856 is connected to the LD100 over the SPI interface. Once the device type is selected, you can start reading the temperature.